Oh. I was actually aiming for the second. I know it was going to the trash can. Oh, is that the Jeremy
All right, so we're going to talk about comparison of series. A couple of different ways we can compare two series. The first one, let's get started. First one, direct comparison, my favorite. Direct comparison is exactly like it sounds. So we're going to say that 0 is less than, not less than or equal to, less than the terms of one series, and that's less than the terms of another series for all n. We have two tests that we can use here. If the sum n equals 1 to infinity of b sub n converges, then the sum n equals 1 to infinity of a sub n converges. So the way I think about this, b sub n is our series that's up here, and a sub n is down here because b sub n is greater than a sub n. If b sub n converges, it forces a sub n to converge. I think of it like pushing it down. And if we turn the inequality, if we go the other direction, 2, if the a sub n series diverges, then the b sub n series has to diverge. So a sub n is down here, and it's diverging, and b sub n is up here, so it forces b sub n to diverge also. And the reason that this works is that for case 1, if b sub n converges, it puts an upper bound on the sequence of partial sums for a sub n. And that's going to force it to converge. And the second one is the other way. If a sub n diverges, then the sequence it forces the sequence of partial sums to be unbounded. Forces the sequence of partial sums for b sub n to be unbounded, so b sub n is going to have to diverge. Now the thing with direct comparison, the reason that I like it is it really makes you think about how the two series are related, and it makes you think about the relation, the magnitude of each one. So, and it also, the more series that you know how they behave, the more you can use direct comparison. Because you think, oh, well, that's going to be smaller than this series. So I like how it makes you think about the two series and their relationships. All right, I want to make a quick note. Because convergence or divergence is not affected by the deletion of a finite number of sums, we could modify this to say that the test applies for n greater than some integer n, capital N. So instead of for all n, we could say if eventually this is true, then we can apply the direct comparison test. So we're deleting a finite number of terms from the beginning of each series. So eventually, one is always less than the other, or one is always greater than the other. Then we can apply the test as well. All right. Let me look at some examples of applying the direct comparison test. Now, the nice thing about direct comparison is when you can use it, it doesn't take a lot of work. You just have to realize what series to use and how the two series are related, and you don't have to do a lot of manipulation. So we're testing for convergence on all of these. The sum n equals 1 to infinity of 1 over n plus 1, n plus 2. Now what's another a different technique other than direct comparison that we might be able to use here? We might be able to use partial fractions and break it up into a sum of individual sequences. But I'm going to say, looking at that sequence, is there some kind of comparison we can make? I'm going to say that 1 over n times n plus 1 times n plus 2 is less than 1 over n cubed, right? Because we're dividing, our denominator is larger. So term by term, that's going to be smaller than 1 over n cubed. And the sum, n equals 1 to infinity of 1 over n cubed. What do we know about that? That's a convergent p-series. So we have this 1 over n cubed is up here somewhere, but it's converging. And this term by term is less than that one, so it has to converge also. The b sub n, put this here. This is 1 over n cubed. This is just how I visualize it. This is 1 over n plus 1, n plus 2. And if this is converging, then this one also has to converge. So we say, so the series converges. Now, I could also say, so the mistake that sometimes students make is say, well, oh, this is less than 1 over n. Well, that doesn't really help us because 1 over n diverges and it's greater than this. So that doesn't help us at all. We need to think of the series that we compare with somehow pushing the other series either down to some convergence, some finite number, or up to some unbounded number. All right, let's look at another one. And it's nice when we can compare to a nice easy series that we are familiar with. 1 to infinity of 1 over the square root of 2n minus 1. We're testing for convergence. What would be a good thing to compare this one with? I'm going to say 1 over square root of 2n minus 1. What do we want to compare it with? Is Okay, so if we're gonna, and the thing with the direct comparison test, if you're gonna tell me that this term by term is greater than 1 over n, you're gonna need to show me that square root of 2n minus 1 is
1 over 2n minus 1.
it. How do we want to compare?
We could just take a derivative and do the same thing we did.
So are we thinking this is convergent or divergent?
Divergent.
Divergent. So we need the denominator we need this denominator to be smaller? Smaller than the one that we're comparing it to? To make the term to make the wait, do we want it smaller or larger? We want the denominator smaller or larger? We need the denominator to be
Smaller.
The denominator needs to be bigger.
the denominator to be larger, so that the term is smaller than the one we want, right? No, so the larger denominator. We want the small denominator to make the term larger, right? So what are we going to compare this to? So if you want to tell me that this is if you want to compare to 1 over n, you're going to have to show me that square root of 2n minus 1 is less than n.
Could we compare it to 2n minus 1 and then say that it's less than or greater than that, and then say that 1 over 2n minus 1 is greater than 1 over n?
Wait.
Or
Yeah, no, you possibly, but let's think about the easiest thing that we could compare it to. 1 over, how about just the square root of 2n? The minus 1 makes this smaller, so that's going to be larger than that, right? So this is a divergent p-series. The sum n equals 1 to infinity of 1 over the square root of 2n equals 1 over the square root of 2. The sum n equals 1 to infinity of n to the 1/2, 1 over n to the 1/2, which is divergent. So the series diverges. And I'm not saying this is the only comparison you could make. Just to me, this is the one that jumps out that's easiest, so that this denominator is smaller to make this term bigger. Yeah.
The one I said work where you do like multiple in a row, so you say that that's greater than 1 over 2 and n minus 1, which is greater than 1 over n.
A is greater than B is greater than C.
Yeah, you can do. Yeah, you can use a transitive property. Yeah, yeah. So the way I think about this one is this is kind of the opposite direction. So we have one series doing this and one series doing this. This is the 1 over the square root of 2n. No, this is 1 over 2 square root of 2n. And this is the larger one, 1 over the square root of 2n minus 1. So this one is divergent, so it's forcing this one to be unbounded. All right, questions? So this one points out a little bit why the direct comparison is a little bit tricky to use, because you really have to think about the quantities and how they're related and what's going to be convenient to compare, and is it going to be easy to show that one quantity is less than another quantity or one quantity is larger than another quantity? Because if you wanted to, like I said, if you wanted this to compare it to 1 over n, you would need to show me that square root of 2n minus 1 is less than n.
But you could use a transient chain for that.
Yeah. All right. Next test is the limit comparison test. This one is Miss Hines' favorite. And I simplify it a little bit, maybe from the way you might have done it before. So our limit comparison test says we're talking about a series with positive terms. And this is nice because we just look at the limit as n approaches infinity of a sub n over b sub n. If this equals L, where L is finite and positive, then the sum a sub n, and this is the infinite sum, the sum b sub n, either both converge or both diverge. There are other conditions you can say, well, if the limit is such and such, then that means this about this series and that about the other series. One, it's difficult to remember those things. And two, if you try the limit comparison and it doesn't work, there's probably a better way to test the series for convergence than the limit comparison, than remembering all those different conditions. So this is the only way I use the limit comparison test. Just if L is finite and positive, then both converge or both diverge. If L is not finite and positive, then I look for another way to determine the convergence or divergence. All right, this is easy to see. So we're going to say, since both of these are positive, we can say we have the limit as n approaches infinity of a sub n over b sub n equals L. By the definition of the limit, there's some n so that 0 is less than a sub n over b sub n is less than L plus some number, epsilon. Just some number. The definition of limit says eventually we're going to be close to this limit. And this is for n greater than or equal to n. So the definition of a limit says eventually this ratio is going to be close to L. Epsilon means it's as close as we want. Well, this says that a sub n is less than L plus epsilon times b sub n. Well, if b sub n converges, then by direct comparison, a sub n converges. Yeah. And then we can make the same conclusion about the other direction. If a sub n diverges, then b sub n diverges also.
And then when you pick your b sub n, b sum p series equals
yeah, some nice series that you know what it does. So that's the reason we do both of these together, is a limit comparison actually comes from direct comparison. That's why it works. So they're really the same test.
And then the other two special conditions are if you compare to a conversion series, if you get your limit is equal to 0, that's okay. And if you
I honestly, I do not know. I don't remember any of those. This is the only way I use this. Because if it doesn't come out finite and positive, there's a better way to test. Yeah. All right. So the first thing that I want to do here is show that the general harmonic series the sum n equals 1 to infinity of 1 over an plus b diverges. Yes, A and B are just some constant. So this kind of looks like a harmonic series, but we have this kind of linear thing going on in the denominator. And we would suspect that this diverges since the harmonic series diverges. Now, we cannot do direct comparison with the harmonic series here. Why? Yeah, 1 over an plus b, that denominator is larger than n. An plus b is larger than n. So term by term, this is smaller than the harmonic series. So we couldn't do direct comparison. We remember, to show divergence, we want our divergent series to be less than the series we're showing diverges. But could we do limit comparison?
Of course.
Yes. Let's do the limit as n approaches infinity. This is similar to the harmonic series, so let's compare with the harmonic series. 1 over an plus b over 1 over n is what we're looking at. So that's the limit as n approaches infinity of n over an plus b, which equals 1 over a, finite, positive. So the series diverges. Yes.
What determines what other series you want to use?
Something that's nice, something that seems similar to this, something that's going to work nice to find a limit. You probably wouldn't want to do like a logarithmic function or some crazy thing. Something that's nice, something that's similar term by term. Yeah.
Wasn't there also some rule that, like, if it approached infinity and you used 1 over n or something, then they both diverge?
Yeah, that's Kira was saying something. There are other things that go with the limit comparison. I just look at. I think they're hard to remember. This way is easy to remember, and if the limit is not finite and positive, there's probably a better way to decide if it.
Can we use that on a test or something?
Say,
Because I think it's really easy personally.
All you have to remember is that the top grows faster than the bottom. The bottom is divergent series, and the top diverges as well.
Yeah.
wow.
So that the other
That's the
rule,
best
which I'm
proof
pretty
of
sure
that.
actually correct, is if you
So
compare
can
to
we
that
use
earlier
that
series and
both?
you go to infinity, that's
I would have to look at it again. I don't remember that part of the limit comparison at all.
Okay. Because that was like my favorite test.
Disappointed.
Yeah, if it's a valid test, I would accept it,
Okay.
but I would have to look back and see. Because this is the only way, I think this is the nicest way to use a limit comparison, and you don't have to remember a bunch of other stuff. All right. Limit comparison, in general, works when you have a series with complicated algebraic terms. And you want to, in this case, you compare with a p-series. And the p-series that you want to compare with is a p-series that has the same magnitude nth term. In general, that's when the limit comparison test is going to be useful. So what we mean by the same magnitude is and it's not exactly accurate, but we're kind of disregarding all but the highest powers of n. That's not exactly what we're doing, but that's kind of what we're doing. So let's look at what I mean by a series with complicated algebraic terms. So we have something like this. So we want to determine the convergence or divergence of this series. I would say that's kind of complicated algebraic terms. Algebraic means we have powers, we have exponents, but we don't have logarithms, we don't have exponential functions, we don't have trig functions. So the highest power in the numerator, the magnitude of the numerator is n squared. The magnitude of the denominator n to the fourth. So I want to compare with the sum n equals 1 to infinity of n squared over n to the fourth, which is the sum 1 over n squared. Which is a convergent p-series. So I would guess that this converges because it's similar in magnitude to a convergent p-series. And we're going to use a limit comparison test to see, is it similar enough in magnitude to get it to converge. So I'm going to say the limit, I'm going to look at the limit as n approaches infinity of 3n squared plus n over n to the fourth plus the square root of n over 1 over n squared. And why don't I just write that instead of doing the fraction? I'm going to flip it. Multiply right away. So this is the limit as n approaches infinity of 3n to the fourth plus n to the third, n to the fourth, plus the square root of n. And what's that limit? 3. How would you show it? Not by saying the top is bigger than the bottom, or we can ignore these things. Not by doing that. How would we show it? L'Hopital's rule. How many times would we have to apply it? 4 times. L'Hopital's rule. So that equals 3. which is finite and positive. So yes, if you say, oh, if you cross these out and say, or cross all this out and say the limits 3, that's not going to be a good enough mathematical argument. If you could say, oh, I can ignore everything but the first term, that's not going to be a good enough mathematical argument. You need a little more. Yes.
Could we just say we use L'Hopital's and then?
Yeah, you could say L'Hopital's
So you don't have to actually-
L'Hopital's rule 4 times.
Oh, so you don't have to actually.
You don't even have to actually do it. But don't say the top grows faster than the bottom, or the bottom goes faster than the top, or I can ignore this, or eventually this doesn't matter.
When you
Where-
use L'Hopital's, when you get a negative exponent equal to the log root of n.
Yeah, root of n doesn't go away when you use the L'Hopital's.
Yeah, L'Hopital's wouldn't go away. The root of n doesn't go away with L'Hopital's.
But as n approaches infinity, you're dividing by a really, really big number. So you're still okay.
How do you do an abbreviation for L'Hopital's?
LH.
Oh, don't you put, I thought you put comma between L, like the apostrophe between L and
Either way.
Apostrophe.
Either way, I don't care. Times 4.
Perhaps. 2 to the 4.
Can I show you another way?
Yes.
Other than L'Hopital's rule. This is nice when L'Hopital's rule, if you get something complicated that doesn't go away, like Ben was talking about. We could also, another technique you can use is divide everything by the highest power of n. So I divide everything by n to the 4th. This limit, as n approaches infinity, is 0. This limit is 0, and you just end up with 3. So that's a nice little trick to use when you do have those things that switch, like to the numerator to the denominator, and you can't get them to go away with L'Hopital's rule. Divide everything by the highest power of your variable.
So for things like root n, are we safe to say that we know that root n eventually goes to, if you just L'Hopital's, for this you could legitimately just say L'Hopital's 4 times and that's an acceptable.
Yeah,
Even though the root n doesn't go away.
Right. Yeah, that's
But
fine.
we're safe to assume that we know that.
But sometimes you get something that like an exponential or something that you can't that just stays there, doesn't go away, but you think, okay, that limit should go to such and such. Divide everything by the highest power of n, and that's a nice little trick. All right, questions. Okay.
She's not charging membership, Kyle. She's the website activist. She probably knows. You know my coach, and they lowered it. Do you know how we know if we got it?
Guys, I'm excited. We've had a problem with the printer because they haven't been here, so we had to delay everything. So you'll get like a
All right, there we go.